Okay, here is a bridge circuit and it says the bridge is balanced when del R is equal to 0. We can see the four resistances here. R0 plus del R, R4 here, R2 and R3. And it says the bridge is balanced when del R equals to 0. That means when del R is equal to 0, R2 over R3 is equal to R4 over R2 over R3 at balanced condition R0 over R4 when del R is equal to 0. When del R equals to 0, this is given. We need to show that if del R is much less than R0, V0 is this much. So that's not the balanced condition. So we will just try to find V0, write the expression of V0 first. That's how we should do. So V0 is the voltage drop across R4 minus the voltage drop across R3. That will be V0, because this drop, whatever the potential here, we can know by applying voltage divider rule in this so this is the voltage source and these are the two resistances where this voltage, the whole voltage is dropped. So if we find the voltage drop across R4, so VR4 minus VR3 will be V0. So VR4 will be V in over R0 plus del R, that is this resistance, plus R4, so just voltage divider rule, times R4, and this one will be again V in R2 plus R3 times R3. This is what it will be. So we can rewrite this, like we can take the V in out and we can write this R4 divided by R0 plus del R plus R4 minus R3 divided by R2 plus R3 times V in. This is our V0. So what we can see here is this is the expression we need to prove, and here we don't see any R2 over R3 term, R2 or R3 term basically. So what we should do, we should try to get something like this, and then we can replace that with R0 over R3, R0 over R4. So if we can get something as R2 over R3, we can replace that with R0 over R4. So this is now becoming R4. I am not doing any change here, plus del R plus R4. This is the same, but here what I can do is I can divide both numerator and denominator by R3. So numerator becomes 1, this becomes R2 over R3, and this is 1, and then Vn is there. So this thing we can now rewrite R0 over R4. So that's what I will do. R4 here, R4 plus del R plus R0, actually R0 plus del R plus R4, whatever, same thing basically. Sorry, not the bracket is not here, minus, so this is now I will write R0 over R4, so 1 R0 over R4 plus 1, and then V in. So if I write that, it will become R4 plus del R plus R0 R4, and this is now becoming again R4 R0 plus R4 V in. So we will just do the subtraction. So this is now R4 plus del R plus R0 times R0 plus R4, and we have V in there, and this is becoming R0 R4 plus R4 square So basically just the subtraction, and this is R4 square minus R4 square minus del R R4 del R R4 and then R naught R4 R4. So we can see that this is getting cancelled and this is getting cancelled. So we have now minus del R and times R4 divided by this thing R4 plus del R plus R naught times R naught plus R4 and times V in here. But now we have to show that this thing, when we have to show when del R is much less than del R naught. So what we can do, we can actually ignore this part. This is almost 0 because this is much less than R naught. So now it becomes R4 plus R naught times R4 plus R naught. Basically del R terms, that term becomes 0, so del R, but not on the numerator, because of course it won't be, because it's a multiplication, it's small, it matters, but here it is just added with R naught. But since this is, so basically this is the resistance, total resistance, but this is much less than R naught, so we can just ignore that term. That's how in the denominator, it's just pure algebraic thing. We can just ignore del R in the denominator, we can make that 0, and if we do that, it becomes like this. So R4, and this is, it finally becomes what we were needed to prove. So this is the expression. I missed the V in, which I thought I would. So here I will write just like that, V in, yeah. So, and this is V naught, but since we have done here an approximation, so we should, it's almost equal to, because we have ignored the del R term, just because it's much less than R naught, we have made that approximately 0. As a result, this is approximately equal to V naught, and that's what we needed to prove here. So that's it.